Alright, so let's go over your do now, right now. This should be day 10, because yesterday should have been this. So, trace the path of the robot in the maze and mark the destination square. So again, we're supposed to trace the path and mark its destination. So the first line, rotate left. So now it's going to point this way. And then we have a repeat 2. And it wants to move forward. So it'll move forward once, and then it repeats again, so it moves forward twice. Then it says rotate right. So then it's gonna point up, and again repeat 2 times, move forward, 1, 2. Then rotate left. If it's pointing this way, then it's gonna point to the left, because it was pointing up before. And then repeat 2 times, move forward, 1, 2, and then rotate right, so it's going to point up again, and move forward 2 times, 1, 2. So this is the destination square, and the path it takes, it goes like this. Alright, perfect. So let's get into the lab for today. Make sure you have either the back of your paper or something so you can write these definitions. So in this lab, you will explore how models and simulations can be used to gain insight into real-world phenomena. You will learn why models and simulations are used instead of real-world experiments. So models and simulations, there's just like experiments, but instead of doing them like actually hands-on, you do them on the computer. You simulate them. There's a number of reasons this happens. It's because experimenting is expensive, it's time consuming, can be dangerous, and sometimes could be unethical. Like, for example, maybe you want to experiment with some new virus, you don't want to give the population that disease to test how fast it spreads, right? That would be unethical. That would be dangerous. So here for your notes, just make sure you write somewhere. Models and simulations. So a model is a computer representation of an object in the real world. So it's like, yeah, let's say, like it says right here, you have an airplane. You can represent a model of an airplane could be a sprite that you have with a picture of an airplane. That models your airplane. So it's just like a fake to scale or not to scale thing. You have a simulation. This is an algorithm that uses models to see what will happen over time in certain conditions. So yeah, so if you model an airplane, you might simulate wind hitting it, right? If you simulate the planet Earth, you might, if you model the planet Earth, you might simulate the weather that's going on and how it affects the Earth. So they kind of come hand in hand. A simulation occupies or uses a model, and again, they help represent complex phenomena in the real world. They're used to predict or explain real life occurrences because doing them actually are expensive, time consuming, dangerous, and unethical. Um, However, they rarely capture full complexity of real situations, so it's really hard to make an accurate representation of what the wind is like, or to make an accurate model of an airplane. That's really hard. Um, it would be impossible to include all real dependent factors in the model, so researchers make simplifying assumptions in their models. Yeah, so it's more of like an assumption of like more or less, because it's really hard to include all independent factors. Um, so come up with an example of real life phenomena that you think would be impractical, impossible, dangerous, or unethical, and then explain how modeling and simulations can help understanding that phenomena, and then what are some pros and cons. So just think about it for a little bit. If you don't have an idea, just do what I did. Ask an AI to do it. So for example, nuclear reactor meltdowns. Um, Conducting real world experiments to test the safety of nuclear reactors during meltdowns would be extremely dangerous and unethical. So you won't, like, people don't actually go and melt down a reactor, right? Because that would be catastrophic. But a simulation with, like, modeling and simulations can help understand the behavior of nuclear reactors under extreme conditions. So you could simulate how a reactor would melt down and try to create a safety protocol, or safety measures to prevent that kind of disaster. So like I said earlier, climate change. Studying the long-term effects of climate change through real-world experiments would be impractical due to the timescales involved. Simulations can help predict future climate patterns. So yeah, usually like the weather, um, it's predicted through simulations. Another example that I used earlier, pandemic spread. It would be unethical to intentionally release a virus to study its spread and impact on human populations. So you don't want to infect people to see how they react, right? You would use models of people and simulate how it would affect them with that virus, and evaluate the effectiveness of interventions and prepare for the future pandemics. So they help predict outcomes, test hypotheses, optimize designs, and just be prepared for anything, right? And then pros and cons. Pros, you are able to you eliminate that risk factor or that danger factor, right? It's cheap, it's fast, and it's flexible. So the exact opposite of this, right? Real world experiments are expensive, time consuming, dangerous, and unethical. The cons of models and simulations is that they're very simple. So they rely on assumptions like you saw right now. And so they might not be accurate, which is the other one. The accurate simulations depend on the quality of the models. There's limits to what computers can do, and most of the results could be open to interpretation. So whatever uh, the researcher interprets, um, it's kind of hard to really grasp the whole thing to make a better conclusion. They must be used carefully and in conjunction with other research methods to ensure accurate and reliable results. So yeah, right here in the bottom of your notes, make sure you write one example of where you could use models and simulations. Then let's go on to the next page. Oh, so you learn how to model the tossing of a coin. This one's fun. So we'll just put this to the side. When you toss a coin, you assume that the chances of getting heads or tails are equal, but if you toss a coin 10 times, you know that you might not exactly get 5 heads and 5 tails. What percent of the time do you get that result? Is it different if you toss the coin 100 times, 1,000 times? It is tiresome and impractical to toss a coin hundreds of thousands of times, but it's impossible to explore all these questions without a simulation. So you're gonna flip a coin. So pretend that you have a coin right here, and after you flip, it can either be heads or tails, right? That's after the first flip. Then, what if you toss it twice? So if you toss it twice, then you could have another heads or tails. So out of, you have 4 different outcomes. I guess what this is trying to do is what percent of the time do you get the same amount of heads and tails? So for example, here 25%, you have 25% chance of landing 2 tails, right? Because this is tails and this other tails. And here you have another 25% chance of landing tails, then heads. Then here you have a 25% chance of landing heads, then tails. So it's different. And then here you have a 25% chance of landing both heads. And if you do another flip, the chances become lower. Because, for example, if you do another flip right here, you have another heads and tails. So there would be like a 12.5% chance. So this is just statistics, but it becomes increasingly harder to land, for example, tails, 4 tails in a row or 3 tails in a row. Okay, so let's open the snap file, and then we're gonna simulate a coin toss. So to simulate a coin toss on Snap, coin toss sim. First, we need to ask how many flips. Because this is the first step. When and how will the user input the desired number of flips? So that's the very beginning. Then we need to simulate the coin mathematically. So that one is we'll get a random number, between 1 and 2, and if it is 1, then that's heads. If it is 2, then that's tails. So we'll have the computer pick a random number between 1 and 2. If the number is 1, it'll be heads. If the number is 2, it will be tails. And then what will the user see? We'll just change the sprite, whether it's 1 or 2 for heads and tails. What are the variables to create in order to keep track of the parameters? So we'll just need one variable for, so here, variables. We'll need one to keep track of the flips of the random number, random, and then we'll need one for the number of heads, and another one for the number of tails. So let's click here. Yeah, if you click on this button, it'll take you to this coin toss thing, and you see there's a coin that has heads and tails. So on the green flag is clicked, we will ask how many flips. So how many flips? And then we'll store our answer in a variable called flips. So set flips to whatever answer. And then after this, we will repeat as many times as the answer was, and then we'll flip a coin. So to flip a coin, we'll pick a random number between 1 and 2. So we can actually make a new block for this. Let's make it other. Make sure it's a command block. So flip a coin. We'll make a block called flip a coin, and this one we'll pick a random number. So we'll make a random variable, and then set this random variable, set random to a random number between 1 and 2. And then if the random number is 1, the random number is equal to 1, then that means it is heads. So you would switch the costume to heads. Switch costume to heads, and then make a new variable called number of heads, and then another one, number of tails. And then we change. Okay, so we first have to set them to 0. So at the very beginning, set number of heads and number of tails to 0. But after the random number is 1, that means it's heads, so we change the heads by 1. Because that means it landed heads, so we want to know how many times there were heads. Just gonna move this here, that way you can see them here. And then else, that means it was tails, so you do the same but for tails. Tails, change tails by 1. So that's our logic to flip a coin. So make sure you click apply. And okay. Then let's look for the block. Flip a coin. So it'll flip a coin as many times as it's there. And just so we see right here, let's have a wait 1 second. Okay. So let's try it. How many flips? So let's try 5 flips. There was a tails, there was a heads, a tails, a heads. Oh, there were 3 heads and 2 tails out of 5 flips. That's pretty cool. So now let's do 10 flips. Heads, tails, 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 heads, heads, tails, tails, tails. So again, you can see here there are 7 tails and 3 heads. So it's never of, it's a 50-50 chance, but it will never be 5 and 5, or it might be. You can try more flips if you want. So for 100 flips, it'll take like, it'll take a good minute, because we have to wait 1 second. Actually, it would take it off, so I'll just stop it here. So look, after a few flips, we had 6 heads and 7 tails, so that's pretty even. Let's just take away this 1 second, and let's try 100 again. No, there you go, goes faster. Look, so after 100 flips, there was 52 heads and 48 tails. Let's try 1,000. Whoa. So look at the heads and tails numbers, they're pretty even. 504 heads, 496 tails. So that's a pretty close number. So kind of what we expected, right? But yeah, make sure you save this and you turn it into teams. Use your program to simulate causing a coin 10 times. Record your percentage of heads that is observed. Combine your results as a class to graphically display the distribution. So you were supposed to do something like this, it's fine. 100 times, how would you expect the percentage of heads to change? So you saw it how it changed, right? So let's try for 10 flips. We have 6 heads. So there was, for 10 flips, we had 6 out of 10 heads, which is like 60%. And let's see what it says for 100 flips. We have 58 out of 100, which is 58%. So it didn't change much. It decreased a little bit, right? But stayed relatively the same. It didn't change as much. But yeah, so make sure you save this, make sure you turn it in, and make sure you have all this in your notes. So the definitions, make sure you write one example right here, and then the coin toss simulation. But yeah, make sure you answer the exit ticket defining these 2 words, and you'll be done for the first part. Not sure if you're doing this date as well. I'll make a separate video for this. But yeah, make sure you do these 2. Nice.